In this video, we're going to continue our study of oscillatory motion and concentrate on the special case of simple harmonic motion. So what is simple harmonic motion? Well, it's a special case of periodic motion when we have a restoring force that is linear with the displacement. In other words, the force that a spring exerts is an example of this. So if I double the distance that the spring is stretched, the force doubles. If we have a restoring force of that type, where the force is directly proportional to the displacement from equilibrium, then we get simple harmonic motion. By the way, that term harmonic, for those of you who are have some familiarity with music and music theory, you've heard of the term harmonics before. There is a connection there, and if you come back for Physics 2, we'll explore that connection when we look at waves. For now, though, let's look at the example of a mass on a spring. We've said that because it has this restoring force, F is equal to negative kx, that our mass on a spring is going to undergo simple harmonic motion. What we want to do then is to be able to figure out what will the position, the velocity, and the acceleration look like as a function of time. So we want to be able to predict where the object will be or how fast it will be moving, etc., at some time. Now, if we could use kinematics, we'd already know the answer. We know that x is equal to x naught plus v naught t plus 1/2 at squared, and v is equal to v naught plus at, and a is constant for kinematics. Now, all of these are just functions of t, right? So x is a function of t, v is a function of t, a is a function of t. We don't usually use that notation in physics, but just to emphasize, those are the equations that give us position, velocity, and acceleration as a function of time when we've got a case of constant acceleration. As we've already determined, though, simple harmonic motion is not a case of constant acceleration, because the force that the spring exerts on the mass is going to be constantly changing as that mass oscillates back and forth. So we can't use kinematics. What we want to do then is find what is the position, the velocity, and the acceleration as a function of time for simple harmonic motion. Remember, in our previous video, we also talked about what does the period of the motion depend on. Does it depend on m, the mass, k, the spring constant, g, the acceleration due to gravity, and a, the amplitude? So how does it depend on those, and which of those does it depend on? So that's our goal. That's what we want to figure out. X, v, and a as a function of time, and then what does the period depend on? In order to do that, we're going to use Newton's second law. So we know that the net force on an object is equal to its mass times its acceleration. Let's draw the free body diagram for a mass when it's here at its maximum position from equilibrium. So when it's at amplitude A. You'll notice that we've got three forces acting on the object. And by the way, here we're going to stick with the case of no friction. In a later course, you'll study simple harmonic motion with friction, but in this course, we're just going to look at it without friction. So we've got the normal force, we've got the force of gravity, and then we have the force that the spring is exerting. So when we look at this, then you'll notice that the normal force and gravity are going to cancel each other out, and so the net force is just going to be the force that the spring exerts. So I'm going to put on subscripts for the x direction here. This force the spring exerts, FSP, is to the left, so we'll put in a negative sign there, and that's got to be equal to MAX. Now, we know that in this case, that force is not going to be constant because it's equal to negative kx. And so what I'm going to do is I'm going to replace the acceleration with the derivative in terms of x. Remember, the acceleration is the second derivative of position with respect to time. And so this is the equation that we want to solve. And I'm going to rewrite it a little bit. I'm going to write the second derivative of position with respect to time is equal to negative k over m times x. So we want to solve that for x. Now, you may never have seen an equation that looks like this, that has a variable and one or more derivatives of the variable. This is called a differential equation. So a differential equation just is an equation that relates a quantity, in this case x, with one or more of its derivatives. You may be familiar with the basic calculus sequence most of you will be going through. There's Calc 1, there's Calc 2, there's Calc 3, and then the fourth course is called differential equations, or as people say when they take it, diffie-qs. So you're going to spend a whole course learning how to solve equations like this. What I want to do, though, is show you that for an equation, a differential equation that is this simple, we can probably figure it out without taking a whole course on differential equations. We just have to remember a little bit about derivatives. So one of the ways to solve differential equations is simply to do it by trial and error. So let me show you an example of this. I'm going to give you a slightly simpler version of that differential equation. Let's say it's dx squared, or d squared x dt squared, is just equal to negative x. So for the moment, keeping the k and the m out of it. I want you to think about, what is this equation asking you to do? Remember, every equation is just kind of asking you a question or telling you a story of some sort. So this equation is posing the following question. What function do you know that if you take the derivative twice, you get back to negative the original function? Okay, so I've given you some choices here of some functions that may satisfy this differential equation. Go ahead, pause the video, and see what you think. Okay, well, the correct answer is D. And just to show you that, let's take the first derivative, dx dt, and then the second derivative, d squared x dt squared, of each of these functions and see what we get. So the derivative of cosine is negative sine. The derivative of sine is cosine. The derivative of e to the minus t is minus e to the minus t. Let's now do the second derivative. So derivative of minus sine is negative cosine t. The derivative of cosine is negative sine t. And the derivative of negative e to the negative t is e to the negative t. So what I want you to notice is, remember, we're looking for a function that when we take the derivative twice, we end up with negative the original function. So notice here we have cosine t. When we take the derivative twice, we have negative cosine t. So that one definitely works. We start here with sine t, take the derivative twice, we get negative sine t, so we got negative the original function. That one works. E to the minus t, however, doesn't work, because you'll notice we didn't get back to minus the original function. In fact, e to the minus t, you'll notice, would be a solution if this minus sign weren't there. So that's not a solution, and that's why the answer is just A and B. So based on that, it turns out that the solution to our differential equation is x of t is equal to a cosine omega t. And you'll notice the only thing that's different than kind of that simple version we just looked at is we've put in a couple different constants, a constant a and a constant omega. Also, although sine would also be a solution, it turns out for simple harmonic motion, cosine makes more sense because when t equals 0, we want to have displaced the mass. And obviously sine is 0 at t equals 0. So let's go ahead and see what we can learn from this solution and see actually if it is even a solution. In order to test whether this is a solution of this differential equation, all we do is take the derivative twice. dx dt is going to be equal to negative omega a sine omega t. Remember, by the way, in physics, we often don't put those parentheses in, but they're there. We just don't usually write them. Okay, so that's the first derivative. The second derivative, d squared x dt squared, is going to be negative omega squared a cosine omega t. Notice, by the way, when we did that derivative, we had to use the chain rule. So we took the derivative of the outside function, which was cosine, but then we had to take the derivative of the inner function, omega t. And again, we're differentiating with respect to t. So t is our variable, a and omega are constants. All right, so now we're going to take what we just learned and plug it in to our differential equation and see what we learn. Remember, we've said that for simple harmonic motion, this has to be true. The second derivative of the position as a function of time has to be equal to negative k over m times the original function. So let's put in what we got. On the left-hand side, we got the second derivative. That's negative omega squared a cosine omega t. And then on the right, I have negative k over m times the original function, which is a cosine omega t. If we look at this, you'll notice that a and a cancels, cosine omega t and cosine omega t cancels. And so what we get, and actually I can cancel out the negative signs too, what we get is omega squared is k over m. So here's what we've learned. X equals a cosine omega t is a solution only if omega is equal to the square root of k over m. Okay? So x equals a cosine omega t is a solution only if omega is equal to the square root of k over m. So what does that mean? What have we learned? Well, first of all, remember what omega means. This is something that you've seen a number of times in math, and that is that when we write a cosine omega t, that omega is a shorthand for 2 pi times the frequency, or 2 pi over the period. Remember, the whole idea here is when I want a cosine or a sine function to be periodic over something other than 2 pi, what I do is I write 2 pi over the thing that I want it to be periodic in. So in this case, it's just the period capital T times our variable. So omega is just a shorthand. We call omega the angular frequency. And again, what we've said is that if this is going to be a solution, if this actually describes simple harmonic motion, then omega has to be equal to k over m. So at this point, what we know is that a cosine function would describe simple harmonic motion. Notice that our value here would be a, the amplitude, and down here would be negative a minus the amplitude. And we know that it would repeat every period t. But let's dive in and see, what does this tell us? Well, what we're really interested in is the period of the motion. So let's go ahead and take these two equations for omega and eliminate omega and instead write it in terms of the period. So 2 pi over the period has to be equal to the square root of k over m. But cross-multiplying, that means that the period has to be equal to 2 pi times the square root of m over k. And you'll notice that by solving our differential equation and looking at that condition for it to be a solution, that omega had to be equal to the square root of k over m, we've solved one of the big questions that we were asking, which is what does the period depend on? So this is interesting. Notice that the period is directly proportional to the square root of m. The period is directly proportional to 1 over the square root of k. More importantly, notice no a in equation. So in other words, the period doesn't depend on the amplitude. And that's one of the things that we were trying to show. Notice that if we were to plot the period of the object's motion versus the mass, it would look like a square root function. Or if we plotted t squared versus m, it would look like a straight line. Now, one of the things that we haven't looked at is how about if instead of having the object horizontal, what if I hang that mass vertically, where now it's going to seem like gravity might have an impact on it. So let's look at that. Let's say that here is the initial equilibrium position of our spring. If I now hang a mass on the spring, that mass is going to now have a new equilibrium position. So in other words, this is not when the mass is oscillating, but just when it's hanging at rest after we've put it on the spring. The amount that the spring will stretch down to the new equilibrium position, I'm going to call x naught. And let's just figure out what the value of x naught is. When our mass is stationary in its new equilibrium position, you'll notice that we only have two forces acting, the force of gravity acting down, and the force the spring exerts acting up. Since the spring is stretched by a distance x naught from where the original equilibrium position of the spring is, that force would be kx naught. Using Newton's second law, we get that the net force in the y direction is ma(y). Again, here is the new equilibrium position, so there's no acceleration. And we find that just kx naught minus mg has to equal 0, or kx naught is equal to mg. So one of the things that we see is that where the new equilibrium position is does depend on the acceleration due to gravity. But now the question is, does the period of motion, once we start this object oscillating, does that depend on g? That's what we want to look at next. So in order to think about this, again, here was the original equilibrium position of the spring. Here is our new equilibrium position, which is a distance x naught down from the original equilibrium position. And what I now want to do is displace that mass some additional distance down so that when I let it go, it will start to oscillate. And I'm going to call that distance x. By the way, in this problem, I'm treating down as the positive direction just to keep it a little bit simpler. So what we want to do is use Newton's second law. F net y equals ma(y). And I want to look at what forces are acting on the mass when it's right here. Of course, we have the downward force of gravity, mg, and then we have the upward force that the spring is exerting. Notice that that would be k x plus x naught, because the total amount that the spring is stretched is simply x plus x naught. So we have mg down, and again I'm treating down as positive, minus the force up, which would be k x plus x naught, is equal to m d squared x dt squared. And so here is our new differential equation. Now that differential equation looks more complicated, but let's do a little bit more simplification. We have kx minus kx naught is equal to m d squared x dt squared. But remember, we showed on the previous slide that kx naught is mg. And therefore, since kx naught and mg are the same thing, notice that this term and this term go away. And my differential equation is now just negative kx is equal to m d squared x dt squared. Well, that's the same equation that we had for a mass on a spring in the horizontal direction. So same diff eq as the horizontal situation. Well, if it's the exact same differential equation, then it has the exact same solution. And so what we've shown is that the position, whether we're talking about a spring oscillating horizontally or vertically, would still be a cosine omega t. Also, notice that the period would still just be 2 pi the square root of m over k. So although the acceleration due to gravity would change that initial displacement to the new equilibrium position, it would not change how the object oscillates. So if you take a mass on a spring and bring it to Mars, displace it, it's going to oscillate with the exact same period that it would here on Earth. In our next video, we'll summarize what we found here today, and we'll see how we can apply these formulas to problems involving simple harmonic motion.